geometry friends, we are still in chapter 5, and what we're going to look at today in section 5.4 is the indirect proof. So the indirect proof has associated with it the following vocabulary terms: indirect reasoning, indirect proof, of course, and proof by contradiction. So a couple of things that we're going to talk about, and I'll give you an example in just a minute, is the fact is these guys are both the same thing. So an indirect proof is when you use indirect reasoning, where you start with the idea that the thing you're trying to prove is false. You say, okay, well, let's say that's not true. Then you use logical conclusions to show a contradiction, which then proves the thing that you assumed was false is true. So again, the indirect proof and proof by contradiction is a proof where you assume the thing you want to prove true is false. Then by logical process, you show the contradiction and thus you prove it to be true. This seems real generic, right? And you're like, what are you talking about? Say it's false and prove it's true and it's true. What? Good. Let's go ahead and look at an example conversation. And I will be voicing Matthew, Kim, Anna, and Jamal. I'm almost positive Friday is not a teacher workday, but I can't prove it. Let's assume that Friday is a teacher workday. What day is our geometry test? According to the syllabus, it's this Friday, but we don't have tests on teacher workdays. We're not in school. Exactly. So that proves it. This Friday can't be a teacher workday. Okay, did you see what happened there? So the kids are talking about this teacher workday. Matthew is almost positive that it's not a teacher workday. Kim's like, hey, let's assume that it is, and let's talk about other facts we know. And isn't our next test this week? And that's what Anna's saying, isn't it on Friday? Yeah, it is on Friday. And you know we don't have tests on teacher workdays because we're not even in school. So Jamal is like the aha dude right here. He's like, aha, see, so that proves it. Friday can't be a teacher workday because there's the conflict, the test. You see what I'm saying? All right. So that's kind of what we're going to be doing. I know that seemed a little weird, but you know what I'm talking about. I think you get it. If not, it'll make better sense as we move on. So this, by the way, guys, is an example of indirect reasoning. You assume the opposite and then prove that the opposite doesn't make any good sense. So then the opposite of the opposite has to be true. All right. I've confused you enough. Let's look at some examples. Well, before we look at some examples, let's look at this key concept block. I think it'll make things a little bit clearer. How to write an indirect proof. Our first step is to identify the conclusion you are asked to prove. Then make the assumption that this conclusion is false by assuming that the opposite is true. Now you're going to use logical reasoning to show that the assumption leads to a contradiction of that hypothesis or of some other fact, such as a definition, a postulate, a theorem, or a corollary. Point out that since this assumption leads to a contradiction, the original conclusion which you were asked to prove must be true. Okay? All right. So we'll do that in this example. We're going to state the assumption for starting an indirect proof. So state the assumption necessary to start an indirect proof for each statement. Let's look at this first one. If 6 is a factor of n, then 2 is a factor of n. So what we have to do is assume that this is not true. This part would be the thing that we're trying to prove. So 2 is not a factor of n. Assume that 2 is not a factor of n. And I hope you guys remember what a factor is. A factor is a number that divides evenly into another number. Just for kicks and giggles, I'm going to talk about this. This is all you need to do to answer the question, but I want to talk about this just a little bit deeper. So if 6 is a factor of n, meaning if 6 divides evenly into n, then 2 should divide evenly into n. That makes perfect sense. And so the argument would go, if we're doing an indirect proof, assume that 2 is not a factor of n, then n is not divisible by 2, right? But since 6 is a factor of n, then 6 is divisible by 2, then 2 must also be a factor of n, therefore 2 is a factor of n because 6 is a factor of n. I don't know if you like that, but that's kind of where we would go. All right, so here's another one. Angle 3 is an obtuse angle. So we would assume that what? We would assume that angle 3 is not obtuse. Or depending on the constraints of the problem, you could also say something like, assume that angle 3 is a right angle or an acute angle, is an acute or a right angle, to say that it's not obtuse, or is less than or equal to 90 degrees. So that's other ways of saying that it is not obtuse. Okay, so we're going to write an indirect proof, and we're going to do that to show the following. Write an indirect proof to show that if this inequality, negative 3x plus 4, is greater than 16, then x must be less than negative 4. Okay, so let's take a look at step 1. We need to talk about the negation of this, or the opposite of this. Well, if x is not less than negative 4, then we know that we're going to assume, right? We'll assume that x is greater than or equal to negative 4. X is greater than or equal to negative 4. So then what do we have? So looking at step 1, we can break it down. X has to be greater than or equal to negative 4, and x must therefore equal negative 4, or x is greater than 4, according to what we have agreed. Now, I don't know why I have a little I there. I know what I have. So let's look at the first situation. Let me erase this so this doesn't look so crazy. So let's look at the first situation. The first situation that we're assuming is that if x equals negative 4, then we know that that should be negative 3 times negative 4 plus 4 has to be greater than 16. But when we do the math, we get 12 plus 4 greater than 16 is not true. Okay, so we know that this can't be the case. Okay, so then we say, okay, well, if x is greater than 4, then we can choose numbers that are greater than 4 to plug into our inequality here and see if it works. And so if I choose numbers that are greater than 4, let's say, numbers that are greater than negative 4, my bad, numbers that are greater than negative 4, let's say, like, I don't know, 5. Let's just do 5. 5 is greater than negative 4, right? That looks like negative or equal to. Let me make this better. So we're considering x greater than negative 4, and I just chose 5 kind of at random. I get negative 15 plus 4 is greater than 16, and when I do that, I actually end up with a negative 11, and a negative 11 is clearly not greater than 16, and I can just continue to put a bunch of numbers in here that satisfy this, x being greater than negative 4, and I'll see that it does not work. This is negative 11. It looks terrible. All right, so you guys are getting, so then this is also not true, and therefore, step 3, we're going to assert the thing that thus x has to be less than negative 4, given that circumstance. I'll be honest with you, like, even as I'm writing this proof, and this is generally kind of what the textbook has, I don't feel like this is a super tight proof in terms of, well, if I understand the logic behind it, it doesn't feel great to me. I'll just be honest. So if you're not feeling great about it, I get it. Not that the logic is not sound, but it feels a little bit loosey-goosey. It's like, well, what about this? Or what about these things? Especially in math, you can't try every possible number. You can't like try every number. So by me saying, oh, well, what if x is greater than negative 4? I can't try every possible number greater than negative 4. So technically, this isn't a great proof. But this has that indirect proof idea, and so that's what we really want you to demonstrate or see. Okay, so Javier asked his friend Christopher the cost of his meal and his date's meal when he went out for a date, when they went to dinner for prom. Christopher couldn't remember the individual costs, but he did remember that the total bill, not including the tip, was over $60. So we're going to use indirect proof and indirect reasoning to show that at least one of the meals costs more than $30. Let x be Chris's meal, and let y be his date's meal. The cost, I should say, his date's meal, and both of these are cost of. All right, so I think this might be all right. So then what we know is that x plus y was greater than 60. How come? Because it says not including the tip, it was over $60, right? So x plus y is greater than 60. We need to prove that either x is greater than 60 or y is greater than 60. And so I'm going to do step 1 of our indirect proof, which is to assume that both were less than 60. Well, I'm sorry, that's a lie. It was $30. I apologize, Chablitos. You knew it and you were like, this woman, if I could reach through the screen and shake her, I'd let her know that what we're talking about. All right, so 30. My bad, my bad, my bad, my bad. All right, so let's try it again. So we want to prove that either X is greater than 30 or Y is greater than 30 given the information that we have. One of them is greater than 30. So we're going to assume that both are not. So, given this information, let's assuming that X being less than or equal to 30 and Y being less than or equal to 30, what I know is that I'm going to have four distinct situations that could happen. If this were the case, then either both of them were exactly $30, where X plus Y would equal 30, right? But that's a direct contradiction to this because we are assuming that X plus Y is greater than 30 as per Chris's announcement, proclamation. So this cannot be the case. This is not the circumstance that's happening. Let's say that X is equal to 30 and Y is less than 30. Well, if X is equal to 30 and Y is less than 30, I'm going to write it like this, right? You remember we can add the same thing to both sides, right? And if I add the same thing to both sides, meaning 30 and X and 30 are the same in this situation, then that means that X plus Y has to be less than 60, which is the opposite of what we talked about. So this can't be the case. Similarly, I can start off with X being less than 30 and add the same thing to both sides, the Y and the 30, since those are equivalent. And then X plus Y is less than 60, again, a false conclusion given the fact of what we started off with. And again, I can just add X plus Y and that they're both less than 30. So that's less than 60, less than 30 would be less than 60. And again, this is a false conclusion. So since we have false conclusions all the way around, if we assume this to be true, this cannot be true. This should be step 2, by the way. Step 2, where we were using our logic. This cannot be true. Therefore, we know step 3, that X is greater than 30 or Y is greater than 30. Has to be, given the fact that we tried all possibilities where that was not the case. So here's our final example for indirect proofs in number theory. We're going to write an indirect proof to show that if X plus 2 is an even integer, then X is an even integer. If I add up two numbers and it's an even integer, then X is an even integer. Again, it gets a little shady if I start like just writing like, oh, let's say X plus 2 is 6, which is even. Like, you can't do it. Mathematical proof should not be done for one specific number because it's not a proof. It just proved it for that number. It did not prove it for all numbers in that category. So let's think about what an even integer is, right? An even integer is going to be any integer that you can write in this form, 2n, right? Where n is an integer. So anytime you can write a number in the form 2n, that's 2 times an integer is an even integer. And then 2 times an integer plus 1 is odd. So this is even and this is odd anytime we're dealing with n as an element of the integers. So with that in mind, let's get started with our proof. First thing we're going to do is assume that x is odd. Even though x plus 2 is an even integer, we're going to assume that x is odd. If that's the case, that tells me that x is equal to some 2n plus 1. And if that's the case, that means that x plus 2, which we know to be even, can be written as 2n plus 1 plus 2. I can rearrange this, so that's what x plus 2 can be written as, and we know that this is supposed to be even. And so I can rearrange this and write 2n plus 2 plus 1, just changing the way it looks. And I can factor the 2 out from my algebra skills, and I get n plus 1 plus 1. Well, n plus 1 is just some other integer. It's the integer after n, right? Just an integer. And so 2 times an integer is an even number. Plus 1 makes this odd. And that's my contradiction. So we assume that x plus 2 was even. But if x is equal to 2n plus 1, by logic, we see that x plus 2 would have to be odd. So the final step states what we already know. The final step states what we already know. Thus, x cannot equal 2n plus 1, and x must be even. And so that's an indirect proof right there. I hope that this made sense. It was helpful. Let me know if you have any questions, comments, concerns. I look forward to talking to you soon. Take care, guys.